Hello and welcome back. In this video we're going to be proving this theorem 2.8 part 3, which says that if we have an invertible matrix that is scaled, then the scaled version is invertible, and in fact we know a formula for the inverse. So there are a few components to this. So A is going to be invertible, so let's start our scratch work. A is invertible. So that tells us we can get A inverse. Alright, and then we claim that CA is invertible. So let's remember, definition of invertible. There exists a matrix B such that C times A times B equals, put B on the other side, and we should get the identity matrix back. So a few things here. So yeah, actually, let's just try it. Let's try exactly what the theorem claims. Let's try setting B equal to 1 over CA inverse. Then CA times B equals CA times 1 over CA inverse, which is, well, the C and the 1 over C cancel, and the A and the A inverse cancel to I. Right? And similarly, BCA equals 1 over CA inverse, CA equals A inverse A equals I. Right? So everything does indeed work out. We tested it. So here are a few notes that we're going to think about as we prove this. So one is that the introduction of the letter B here was a little unnecessary. We added an extra variable we didn't need to. So really we could start our proof at this point. Okay. And then just a few minor notes. I used the backwards E for there exists. We'd never want to use these symbols in a proof. We only want to use them in our scratch work, and similarly things like ST for such that, and anything else. So let's go ahead and start the proof. So again, we have our hypothesis if A is invertible and C is a non-zero scalar, so we should assume both of those. So let A be an invertible matrix, and C a non-zero scalar. Alright, let's highlight this. Non-zero is spelled in a few different ways. I always use the hyphen. Well, if I'm doing it without thinking, I use the hyphen. A lot of people use it without. Both are generally accepted. Anyway, okay, so let's keep going. A is an invertible matrix, C is a non-zero scalar. Okay. Since A is invertible, its inverse exists, and can be denoted by A to the minus 1. Alright, so that is actually then bringing up this very first part of our scratch work, that A invertible leads to A inverse. Alright, so we brought that up. Alright, let's just, what should we do next? Should we tell the reader where we're going, or should we just keep going? Let's see here. Let's just go ahead. So sometimes mid-proof you want to do things like claim CA is invertible with inverse 1 over CA inverse. Okay. So sometimes you might get lost in your proof, and it's a good thing to just remind the reader of what is going on and why you're saying things. So we might also want to say, notice, since C is non-zero, 1 over C A inverse exists. Okay, so we did indeed use this non-zero assumption. All right, so let's go ahead and compute then. C times A times 1 over C A inverse. We know what we're going to get because we tested it out in our scratch work, but let's be a little more precise here. Instead of just canceling the C and the 1 over C off the bat, let's pull them out so we can factor out scalars. So let's call this scalar associativity, or commutativity. So we can always pull scalars out. Right? Now we have 1 times A inverse, which we know is I, so this would be substitution we've done. We've substituted I in for A times A inverse. Right? And now we know that 1 times I equals I. Right? So we can call that theorem 2.3 or 2.1, number 4. Okay. So if you've forgotten what that is, it means that 1 times a matrix is always that matrix. Okay. So let's give ourselves a period at the end because we got to where we wanted. Another note, instead of writing substitution here, we can write definition of inverse. Whichever one feels more clear to you. Probably the second one does, because it's a little more descriptive. So similarly, 1 over CA inverse times CA equals 1 over C times A inverse times A. And notice we're going to use the same exact reasonings as we did over here. So this is scalar commutativity, then we're going to do substitution, and then we're going to use the same theorem. So in fact, let's just, since we're doing literally the same things, let's just go ahead and do it all in one line and say following. Well, we already said similar. So let's just say with the same reasoning. All right. Excellent. So at this point, we've gotten to A times B equals B times A equals I. So therefore, CA is invertible and has the desired inverse. And we're done. All right. So let's scroll up so you can see the whole proof. All right. So again, I guess this is an example of how to show something's invertible. You find its inverse and do it. All right. Excellent. Don't forget to do some scratch work and then make it look pretty below. And always feel free to erase and edit as you go. All right. Have a good one. Bye-bye.